In this video, we are going to prove that 1 times 2 raised to the 1 plus 2 times 2 raised to the power of 2 plus 3 times 2 raised to the power of 3 and plus all the way and so on to the n term, which is 2 times 2 to the n is n minus 1 times 2 to the n plus 1 plus 2. Okay, so how can we prove this equation for every positive integer n? So we will use the mathematical induction. So we are going to let Pn be this equation 1 times 2 to the 1 plus 2 times 2 to the 2 plus 3 times 2 to the 3 and plus all the way and so on to n times 2 to the n equal to n minus 1 times 2 to the n plus 1 plus 2. Okay, and then what can we do? We start with the base step. So we start with the base step and we let n to be 1, and then what do we have? We might substitute into the left side. Okay, so we gotta have 1 minus 1 times 2 to the n plus 1 plus 2. And this becomes 0 times 2. Oh, I forget to substitute 1 into here. 0 times 2 to the 2 plus 2, which is 0 plus 2, which is 2. And this number 2 is 1 times 2 to the 1. Okay, if you are not so sure, try to let n to be 2 and let's see if it is in the case. So we have 2 minus 1 times 2 to the 2 plus 1 plus 2. So we gotta have 1 times 2 to the 3 plus 2, and it turns out to be, okay, let's see, we gotta have 2 to the 3, right? 2 to the 3 is 8 plus 2. So what is 8 plus 2? Is 2 plus 8. What is 2? 2 is 1 times 2 to the 1 plus 8. 8 is 2 times 2 to the 2, which is in the case. Okay, so in the case where n1 is 2 and n2 is 2, we gotta have p1 and p2 are both true. Now, let's take a look at inductive step. So what can we do with inductive step? For inductive step, we gotta assume that, well, we have to assume that P of k is true. Okay, P of k is true for every integer k such that k is less than m and m must be greater than or equal to what? Equal to 3. Okay, because we already have the case where p1 and p2 are true, so I'm trying to show that when m is greater than or equal to 3, and we assume that, and we have to try to show that P of m is true. Okay, so this is strong induction in which the assumption of the inductive step is the case where P of 1, P of 2, all the way to P of m minus 1 are true, and try to show that P of m is true. Okay, and in this case, I let m to be greater than or equal to 3. When m greater than or equal to 3, we gotta have k less than, it can be less than 3, less than 4, than 5, than 6, and try to show that p of 1, p of 2 all the way to p of m minus 1 is true, and show that if these p are true, and try to show that p of m is true. Now let's get started. So since p of k is true, okay, for all positive integer k such that k less than or equal to m and m is greater than or equal to 3. So what can we assume? So we can use that p of m minus 1 is true, right? Okay, p of m minus 1 is true, okay, and claim that p of m is true, okay, and claim that p of m is true. So we need to start with the case where p of m is true. So what happened? Okay, since p of m minus 1 is true, so we gotta have this. We can substitute m minus 1 into here. So we gotta have 1 times 2 to the 1 plus 2 times 2 to the 2 and 3 times 2 to the 3 and plus all the way to m minus 1, 2 to the m minus 1 equal to m minus 2, 2 to the m plus 2. Okay, and we try to show that p of m is true, so we have to begin with this. So we consider this term, we need to add one more term. So we gotta have this term right here and add one more term, which is m times 2 to the m. So what happened to the left hand side, to the right hand side of this equation? This term becomes m minus 2 times 2 to the m plus 2, and then you plus m times 2 to the m. Okay, and then so I'm going to factorize this term. So what do we have? We gotta have 2m minus 2 times 2 to the m plus 2, and then we gotta have, we factorize this number 2 here, okay? So we gotta have m minus 1 times 2, 2 to the m plus 2, so we're gonna have m minus 1 times 2 to the m plus 1 plus 2. Okay, it looks like we have this one, which is p of m, right? Okay, so we have p of m already, okay? So we have proved that, okay? P of m is true, okay? We have proved that p of m is true. So therefore, by strong induction, okay, this equation, okay, this equation is true, okay? These equations hold for every positive integer n, okay? So we have proved that this equation holds for all positive integer n. And that's it for this video.